So welcome everyone to the first talk of the Chromatic Nullstellensatz seminar. So yeah, we are starting from the basics of stable homotopy theory. So the first few talks will be quite basic in nature, and we'll move on then. Right. So the first talk, yeah. So I'd like to kick off this seminar by an introduction to spectra and localization. So really basic stuff. And at the same time, I won't be going through the details of everything, but yeah, I'll try to keep it as complete as I can, right? So yeah, I was supposed to write a plan, but so I've not written a plan. So the plan is that I'll just talk about spectra and generalized cohomology theories, how spectra are born out of generalized cohomology theories, which we'll just call cohomology theories, right? Right, and then give a few examples of spectra first. Then I'll just basic stuff, and then I'll talk about Gauss-field localization. I give a few examples of that as well, right? So we'll start from absolute basics. So I don't need a plan. Let's start from absolute basics. Right. So yeah, what are spectra and why do we care about spectra? So historically, spectra were born in the thesis of Lima, who was a student of Spania, and so it was an attempt to study stable phenomena. Stable phenomena. So when I say stable phenomena, it is like let me pause for a second and make sure everything's going all right, just to check. Everything seems to be fine. Let me continue. Okay. So I was talking about stable. So what do I mean by stable phenomena? Stable phenomena is like something. So a phenomena. So right, if it occurs in any sufficiently large dimension, and if it occurs in the same manner, irrespective of the dimension. So that is that's the rough idea. What I mean by stable phenomena, right? So an example is the Freudenthal suspension theorem. So that is one of the first stable phenomena that was observed, right? So I'd like to begin. So instead of beginning by talking about cohomology theories, I'd like to begin by defining spectra. So it doesn't make much of a difference, but right. So spectra. So let me call this E. Yeah. By the way, if there is, if there's anything that I mess up, or if there's anything that I get wrong, please feel free to point out. Because I don't have any notes or anything, so I'm just right. So it is a sequence of spaces. So this is the way I denote it. And these are pointed. That I equipped with structure maps. Or spectrum, my bad.
I can't see any text that you're writing.
Wait. Can't see anything? Let me get out of this. Thanks for pointing out. I was kind of concerned about that. Is it? Can you see my screen now?
Now I can see the text.
Yeah, there seems to be something wrong with the full screen thing, but okay, so I'll write like this, right? Thanks. So right. So this is where I just started right now. So I'll define a spectrum first. So a spectrum is a sequence of spaces, which are pointed, of course, that I equipped with structure maps. Right. Which obviously are adjoints, as we know. So this is my notation. This is the way I like to This is the kind of notation that I like to use. So yeah, it's obvious that both of them are adjoints. So right. Now we have this. We have this adjunction. Right. So yeah, I don't need to. Yeah, I suppose I don't need to get to all the details. Yeah, let me go ahead. Because there's a lot that I would like to cover, right? Okay, so now, so when these ones, right, and these maps, so when these weak homotopy equivalences, then the spectrum is called an omega spectrum. Weak homotopy equivalences, then E is an omega spectrum. Right. Okay, so what do I mean by a map of spectrum? So yeah, that is the thing. Yeah, we'll define next. So map of spectra. So okay, let me call this H from E to F is a collection of these continuous maps of pointed spaces, continuous maps of pointed spaces. So right, says that for n. So yeah, right. So we have the following commutative diagram, which commutes up to homotopy. F. Right. So this diagram commutes up to homotopy. Right. So before talking about examples of spectra, as we generally do before talking about examples, we'll first see that there's a faithful and essentially surjective functor from the category of cohomology theories to the homotopy category of the category of spectra. Right. So we'll talk about generalized cohomology.
I'm sorry, but do we really need for these maps to be defined for each n? Maybe the correct notion is that it is defined starting from some n large enough.
Right. So, wait, you're saying that we need to do, yeah, for
I think we
see.
can have a meaningful map of spectra which is not defined for some small
Right.
dimension.
Yeah. Right. Yeah. That's right. Yeah. Maybe I should have said that. Yeah. Not. Yeah. For necessarily. Yeah. I should. But yeah. Thanks. Yeah. I had that in mind, but for some reason I just wrote that for all n. Oh yeah. So yeah, I should say that for necessarily and necessarily large, right? For yeah. Thanks for pointing this out. Right. So yeah. Now I'll talk a bit about cohomology theories. So yeah, I'll just write the definitions. So yeah, I won't spend a lot of time. It's mostly familiar stuff. So a cohomology theory. So let me denote this by H. There's a contravariant functor from the category of CW pairs to the category of graded abelian groups. Z graded abelian groups equipped with the natural transformation, that is the connecting homomorphism that we call with the natural transformation. So can I call this side? So yeah, this just means so. Right. So these are the connecting homomorphisms that such that the following instances are satisfied. So yeah, I won't talk a lot about any of them. So mostly standard things. So the following axiom. So let me start with the excision. So yeah, I can just start by defining a reduced cohomology theory, but yeah, I'd like to. That's not the point. I'd like to begin by cohomology theory. So when you're talking about right, we'll see. So so yeah, what is the excision axiom? So you take a CW pair.
Sorry, can you show again the definition of connecting homomorphism, please? And what is X, comma A?
So it's a CW pair.
Yeah, but perhaps I didn't understand. So it was supposed to be a functor from pointed topological spaces or CW complexes to graded abelian groups, or is it a functor from CW pairs?
Category of CW.
I see. I see.
Yeah. Yeah, you can. Right. So yeah, when I'll talk about you can say that when I'll define a reduced cohomology theory, I'll say that it is a functor from the category of pointed CW complex. I mean, yeah, so you get the point. So yeah, for a CW pair, and you have another, right? You take Z such that so it is the closure, it's interior of A. So the inclusion map. So these are like now basic Heisenberg-Steenrod axioms. So I'm just writing off for completeness. Right. So yeah, this inclusion map induces an isomorphism. So yeah, I'll try to go through this a bit quickly because it may end up taking a lot of time. Right, so this is the excision axiom. So then, so maybe the second one, I'm not going to be homotopy invariance. So for homotopic, so you take a homotopic map. For a homotopic map, okay. This map is isomorphism. Right, there are many different ways in which you can state that Steenrod axioms. So, yeah, but all of them end up being equivalent. So, it's a nice.
By the way, I'm so sorry to be pedantic, but I think that the map J upper star should go in the opposite direction.
This one?
Yep.
J upper star. Let me pause for a moment.
Because it's cohomology, not homology.
Ah, yeah. Thanks. Thanks. Yeah, thanks. Yeah, that was a bad mistake. Okay, yeah. So this is the isomorphism. Yeah, I may end up doing such, yeah, just the direction of arrows. Thanks. Okay, so right, there's an isomorphism. Then the third one, the exactness. For CW pair, we have an induced long exact sequence. So I'll write it down properly. Right. And so then, right. So then the cohomology theory is said to be additive if it takes coproducts to products, which means, right, I mean, naively speaking, right? So okay, let me write it to this. This is equal to product. Right. Then is an iso. And the cohomology theory is said to be ordinary if right. So now for our purposes, so a cohomology theory, when I say a cohomology theory, I mean an ordinary additive cohomology theory, right? So I assume all these axioms are satisfied. So now I'll define reduced cohomology theory. So reduced cohomology theory. I can just say things, but okay, for completeness, okay, let me write it. A reduced cohomology.
Sorry, I didn't quite catch the definition of ordinary cohomology theory.
Mm-hmm.
Oh, okay, thank you.
Thank you. Sorry. Yeah, I should scroll down that fast. Thanks for pointing out. Yeah, I'll try and scroll down a bit slowly. Yeah. So a reduced cohomology theory. So let me denote it like this. Using a tilde is a contravariant functor from the category of based pointed CW complexes to the category of graded abelian groups such that which are of course equipped with natural isomorphism, that is the suspension isomorphism. So let me call this zeta. That satisfies the exactness, homotopy, invariant axioms, and the additive. Additivity or axioms, right? So, but yeah, let me write them down. Oh, is there a question? Oh, I think someone's mic is on, I guess. Okay, so yeah, for completeness, exactness. So yeah, when I'm talking about exactness for the reduced cohomology theory, we have this. We use the mapping cone construction. Right? We have so for CW pair. So yeah. Let me pause for a moment. Well, let me write it down properly. So for a CW pair, we get a long exact sequence that is induced by the following inclusion map. So okay, let me call the inclusion map F. Right. From so say from right into X. And the mapping code includes, yeah, I think I've got this right. Right, so this is the long XX sequence that is induced. Right, and how does the homotopy invariance axiom look like? Everything looks familiar. So, right. Also, so yeah, again, for homotopic maps, so let me put an F and F dash. We have, right. And similarly, we have the additivity axiom as well, which I won't write. Right. So yeah, we can check that. We can check that is for an abelian group. So right. So maybe I should write this. An abelian group. So say A. So singular. So I mean, just to check that, right, that our definition of generalized homology theories is correct. So singular homology with coefficients and okay, A. Okay, so A is my abelian group. Sorry. A is homology theory. Right, so the way we have defined it, and similarly for the reduced version, reduced singular cohomology theory, I want to write this is a homology theory as well, reduced cohomology theory as well, right? And we can also prove all the basic properties, right? Like my Vittori's sequence and everything. Right, so yeah, now talk about ground representability. So yeah, let me write the theorem first. So this was in the 60s, I suppose, 62, I suppose. So this was one of the first kind of results that kind of, I mean, yeah. So we'll see that this has a lot to do with the notion of a spectra. So, right, let me write it down for homology theory. So as I've said, so now from now onwards, cohomology theory is an additive generic cohomology theory. So for a cohomology theory, say H, there exists a sequence of pointed spaces. So say Hn with weak equivalences. So say, let me call this lambda n, such that right. So yeah, so you always have such a wait, should be subscript. Right. So yeah. So using this we get the following. So using ground representability, we can check that. Yeah, I'm just writing some things out, which do not need any explanation. So this is, I have defined this weak equivalence is lambda n. So we apply that. Right. Right, and we are just using the properties, the fact that these are adjoint. Now, right. So yeah. So now we have, as we all know, we have a category of spectra. So we'll denote the category of spectra. So maybe notation, category of spectra, SP. So now let me briefly talk about spectrification. So okay. So yeah, so it is like to every for every pre-spectra, as you say, pre-spectra, that is, you have this sequence of spaces, appointed spaces, and these maps. So for every pre-spectra, you are getting a spectra, right? So that is what it means, what spectrification means. So we can associate. So okay, instead of because I've now defined pre-spectrum, let me write it like this. In each sequence, so say E of pointed spaces with maps. So this is maps on omega spectrum. So maybe a definition. We can associate to each sequence of pointed spaces with these maps, right? An omega spectrum. Right. So yeah, I'll get to the construction. Now, right. So if the adjoint is if the adjoints, all these adjoints that we have are inclusions, then we can define the spectrification. We can set. So this is the case that I talked about. So we denote this spectra by L of E. So E is our original pre-spectrum that we have, or the sequence of pointer spaces with these maps that they're equipped with. So we can define this to be, we can set to be the co-limit of the following diagram. I better not. Yeah, I will write all of these maps. Right. So that is like, so if you write it, so we can write it as a co-limit. Right. So now maybe just a remark. So yeah, as I've been saying, so yeah, I won't be talking about anything in length. So just remark. So right. So if you consider the suspension spectrum, so the way you can get the loop space construction. So yeah, so just remark. So it's pretty straightforward to see if the sequence of spaces of maps or spaces and maps or the pre-spectrum, anyway, like it. Suspension spectrum. So right. If it's a suspension spectrum, then so E, let me call this E. That's the free infinity loop space construction. And we can also write this using the configuration replacement. Right, we can also write it as follows. Configuration replacement. Right, we can also write it like this. So now finally, some examples of spectra. So starting with the most simplest one of all. So Eisenberg midline spectra. So ordinary cohomology with so I'm writing the cohomology theory first with coefficients in some abelian group. So say A. Right. So this is a.
I'm sorry. Can you explain what is a suspension spectra? Because you said that loop spectra or omega spectra is the one where the maps from En to omega En plus 1 are weak equivalences. But by adjointness, the same holds from the map from sigma En to En plus 1. So what is the difference between suspension and a loop spectrum?
So wait, if I understand the question properly, so for an omega spectrum, the map, the suspension map that you have, that is there's a weak right? So yeah, what is the question again?
What is a suspension spectrum?
The suspension spectrum. Oh yeah, as I've defined this. As I've defined this loop spectrum, you're talking about the suspension spectrum, right? Is that a question?
Yeah, because you said that for suspension spectrum you have something right here. Right
I think suspension spectrum is where your nth level space is actually the suspension of some space, but in a omega spectrum, there's a weak equivalences.
Yeah, that is the additional one that we need.
Suspension spectra is just that equality instead of weak.
Yeah, just right. Okay. That's okay. Sorry.
But because before it just didn't make much difference.
Yeah. Sorry, I didn't understand it towards the last. Yeah, thanks for interviewing. I would have wasted more time. Right. Yeah. So yeah, thanks for the question. So all right. So this is represented by. So the spaces are Eisenberg midline spaces. So okay. Because I'm used to writing G, so okay, G is our abelian group. Sorry. Just went. Wait, this seems to be, it should work now. Yeah. Right. So this is one example. Then as you pointed out, we also have suspension spectrum, but I won't write it. So we'll talk about one non-trivial one at least. So okay, let me talk about complex case. So just one, yeah. There are also other ones like complex covariatism, right, and other ones, but yeah, I'll just talk about one. Just an example. So you have this BU spectrum. So right, so by Bott periodicity we have, we know. So just I'm not getting into the details. So, talk about this later, but right. So using Bott periodicity, right? Well, we have this, right? So right, so this basically means that you can just rewrite it as follows. Yeah. Wait. Let's apply the loop here. That should be right.
Sorry, what is Z in this context?
Sorry?
What is Z? I mean, integers.
Yeah.
Well, what is this? Is it type
And
of
this is the
spectrum?
this is the no, I'm just stating Bott periodicity, complex Bott periodicity. And using this, you will see. Wait, let me complete this. So the complex K theory is represented by. So yeah, as I said, we'll talk more about this later. So just to give an example. So it is generated progress. Right. So yeah, I won't talk about other ones. So just an example. So right. Moving on.
The question was, what do you mean by Z?
Z is Z, yeah. These are integers. I'm just using Bott periodicity.
Like a discrete space, or like KZ1, or in what context?
Wait, sorry?
Once again, what is Z? Is it a discrete space, or
So right, so this is the spectrum BU, and Z, as you're saying, yeah, I think that's right.
okay.
Yeah, I didn't give, when I was thinking of it, I didn't give this much of a thought. I just, yeah, I think that's right. Okay, so yeah, let's move on. So, right, so now we'll talk about homotopy groups. So, yeah, I'd like to just define homotopy groups for spaces as well, but that's not the goal, but yeah, just for sake of completeness. So for a space X, then of X is the set of homotopy classes of maps from S to X. Let's send the this function. Send the base point of the circle to a fixed point. Fixed point X. Right. So now we are interested in homotopy groups of spectra. So let me define it. So this is the classical notion of homotopy group. So yeah, this is maybe not needed, but yeah. So for a spectrum, so let me call this H. Right, and you have these sequences. This is the sequence of spaces, and these are the maps. Right. The nth homotopy group of H is the colimit. So it is this colimit right here. The K is a positive integer. Right. So yeah. So now a few examples. So yeah, the most canonical one. Yeah, I'll just maybe give a couple of examples. So the canonical one is stable homotopy groups of spheres. Right. So this is the sphere spectrum. So yeah, we'll talk more about this. We'll see. We'll talk more about this later. And for MU as well. Right. Yeah, we'll talk more about this later. Where so here the generator of generator xi, it is in degree 2i. So yeah, I want to talk about just an example. So yeah, so now let me define a homotopy category. Right. Okay. So for category X and subcategory. So subcategory, say Y, if all isos of X are in Y. Right. And we have this 2 out of 3 property.
Sorry, I have a quick question.
Yep.
So you were writing the homotopy groups of MU, the cobordism spectra, right?
Yeah.
Do you have so maybe it's just your notation. It looks like you have finitely many generators of that ring.
No, there are not. Okay, maybe I didn't write this properly.
Yeah, I thought it was infinite.
Yeah.
Thank you.
Sorry. Yeah, that's just sloppy writing. Thanks. Right. So yeah. So all the isos of X are at Y, and if so, these maps, these are any maps, right? So these satisfy the 2 out of 3 property. Like if 2 of them are in Y, then the third one is also. Right. So then the homotopy category of X is so if it exists, of course, is a category which we denote like this. And you also have this functor. Right, such that, so, okay, let me name this F. If you have this functor which maps Y to isos, so we have this following diagram. Let me draw this. Talk about this. So, okay, let me see. Call this I. So there exists a unique map here. So okay, this is F. Call this Fy. Right. Such that we have this. Right. So now, so maybe I'll define a stable homotopy category. So definition. Yeah, and I'll briefly talk about some properties of the stable homotopy category. Again, I won't get into all the details, but yeah, just talk about some properties. So the stable homotopy category is the category. So, okay, let me use some really bad notation just because I'm used to it. Yeah, seems to be a hassle. I can just say SH, but yeah, I'm just kind of used to writing it like this. And yeah, W are the weak equivalences. Yeah, on top. Much about it. So yeah, so now let me state a few properties. So, right, so even before the construction of the stable homotopy, and there are many different ways in which there are different model sets that I'll briefly just mention. There are different models that we have. So this is one of the models. So there were many things that we wanted. So in order to understand stable phenomena, we wanted such a category, and there were these kind of properties that we wanted that category to have, right? So and it turned out that this category had all of them. So yeah, there were many developments in between in course of time as well, and yeah. So, you have to mention the Spanier-Whitehead category and other things, but yeah, I won't talk about it. I'll just cut to the chase. Right, so right, so just writing a few properties. There exists an adjunction. So right, let me write it down. So hope I'm writing this correctly. This will be yeah. Yeah. So right, and the second property. So these properties. So these are abelian groups. This is our category of abelian groups. And yeah, I won't prove anything or talk about anything later. I'm just stating things. Right. So this category has arbitrary small products and co-products. And in fact, finite products and co-products coincide. Finite products and four products coincide. Right. Then you have this the smash product, so you get a monoidal structure. Yeah, I am kind of skipping all of this because of our plans. So there exists a monoidal product on such that right. So what is the notation? Let me check. Okay, just a second. Sigma infinity. Because I have to check the notation all the time because I end up messing up with it. So yeah, A and B are pointed CW complexes. This is the fourth one. Yeah, or oops, yeah, 15. So let me see. Yeah, just a few more things. Yeah, I'll just talk about the triangulated structure and yeah, I'll stop there. There are other properties as well, but yeah, I'm just listing a few of them. Yeah, there exists an internal function object. So you have this internal function object that I denote as follows on this category such that, so for all elements, right. So now it is a triangulated category. So you have this endo functor, right? Where, yeah, what this is. And you also have this inverse, which is just a loop. And what are the distinguished triangles? Okay, let me just write the distinguished triangles. And then you'll have this least long exact sequences that you can born. Right, but yeah, I'll just write distinguishing triangles. So yeah, this is just a cofiber sequence. So okay, this is and so wait. So I hope I don't mess this up. So just yeah, I think this is right. Oh, yeah. Yeah, so that's more that's most of the part of Spectra. So now, yeah, let me just say we also have other categories, right? So we also have other categories. We have right, see such that from the homotopy category, we'll get different models. So some models, yeah, I'll just state some are like you have a symmetric spectra, orthogonal spectra, infinity category of spectrum, other, right? So there are different models. Cool. So it took lesser time than I had expected. So, okay. So now, let me talk about Gauss field localization of spectra. So that's the part of Spectra. Gauss field localization of spectra. So yeah, before right. So right. So the localization of model category of spectra at these. Wait, I was thinking of saying something. Right. Yeah. So yeah, I meant to talk a bit about Gauss field localization. Right. So right. So localization of the model category of spectra. Yeah, we've not touched upon anything. We've not touched upon the Gauss field and the model structure or the other ones that we have. But yeah, localization of model category of spectra at these collection of maps, which become right. So under the smash product, they right. Yeah, let me write this down. So yeah, this is so this is the stable homotopy category of spectra. So yeah, let me first review technicalities. So right, so for say X of the stable homotopy category of spectra. Right. So a spectrum Y is called X acyclic if you smash it, you get 0. Sorry. Right. Okay. So acyclic. And then okay. Morphism. So I was thinking of writing the different definitions, but yeah, let me club all of them together. So morphism, say F from Y to Z of spectra is an X equivalence. So if this is this map that you have, so we should smash it. That's an isomorphism in the stable things. Right. So yeah, this is just equal to SHC, but yeah, just kind of feels more natural to write it this way for the definition. Okay. Okay. So again, now choose X. Our spectrum is called X local if for all X equivalences, say F, you get an isomorphism, iso, and every morphism, say, wait, let me check. Okay, yeah, Z to Y. Out of an X acyclic spectrum Z, so Z is an X, okay, let me write it here. Out of an X acyclic spectrum Z, this is a zero morphism. Right. So another definition. So again, you take two elements, two X and Y. So now this is the main definition. Then on X localization of Y is an X local spectrum, Y, and an X equivalence. Right. Okay. So now, so now let me talk about completions for a moment. Yeah, I don't think I will be able to talk a lot, but okay, let me see. We can start here. So okay, maybe localization.
Sorry, can you return for a moment to the definition of X local spectrum? I'm sorry, somehow I don't understand. What do you mean? Oh, no, okay, I see. I'm sorry, it's a really stupid question. What is the difference between homotopy category of spectra and stable homotopy category of spectra?
Sorry? The stable homotopy category of spectra and okay. Yeah, let me move back a bit. Right. So stable homotopy. Right. So we are working with the stable homotopy category. So when we take we define a homotopy category, and for I didn't get into the details at all. So maybe we can talk about that later. But yeah, you choose if the category is the category of spectra, and you choose suitable weak equivalences, then this homotopy category. This is what we call the stable homotopy category. There are different versions, as I said. This is the one kind of one, right? So yeah, we can Yeah, this is, the thing is that, this is more of a chromatic. I mean, also, I'm not going to like all the details, but yeah, we can maybe talk about that later. Okay, so localization with more spectra. So just an example, and let me see. See, I don't have a lot more to say, so maybe I'll also talk about telescopic localization a bit. I mean, yeah, so this is kind of going a lot ahead, maybe, but just for sake of examples, I'll just define it. Yeah, I won't talk about it a lot. This is just because I have time, so I'll just define it. So this is right. So this is an example of X localization when X is more spectra, right? More spectra. So proposition. So you take a couple of abelian groups, then the following are equivalent. I won't prove anything again, as I said. So these are the following are equivalent. X and Y have same. Oh, okay. Instead of, okay, because I'm not defining cyclicity, okay, let me write them as two different points. Right. So, so if we prime is in the vertical in X, if it is in Y, and we can show, in fact, if I'm not wrong, but yeah, I don't remember the details. I think you can show that this condition that I said and the other one that I'm writing, about to write, that they're equivalent, but I don't remember the details. So yeah, it is a torsion group, but no, I don't think this was a big deal. Yeah, they're equivalent. Okay, let me write this. Torsion group. Precisely, why is. So maybe someone can make a comment on this. I don't have a lot to say. So I think both of them are equivalent.
Sorry, can you state the second point?
Sorry, the second point?
Can you state it? Yes, I'm sorry,
Yeah.
I can't
I'm sorry.
I'm
sorry. No, of course you can't read it. It's really sorry.
No, it's okay. Just
every prime P is invertible in X if and only if it is in Y. Yeah, I'm sorry. Yeah. I mean, graphic tablets are never my friends. Yeah, somehow try. I already have really bad handwriting. I write on paper, so it gets worse when I write it on a graphic tablet. But yeah, I hope it's okay now. Right. So now I'll define what I mean by pre-localization and rationalization. Again, I'm kind of stepping ahead a bit, so I won't talk about the details. We'll talk about later. So just to give an example. So, okay. So so G is abelian group that we're thinking of, if this is right. Wait. I have to think about this as well. I don't remember this properly, but okay, let me write this first and I'll see. Please point out if I write it wrongly. So I think this is slash X. And the part of it would like, oops. I think this is right, but yeah, I'm not sure if there's anything wrong with this. Point out. So, okay. The P-localization of X that we denote as follows. So wait, let me check if I have introduced the right notation. Yeah, okay, so yeah, I've introduced M. So maybe I won't be able to tell you more about this because I'm just giving an example. The rationalization X. So maybe Rushel can take a few questions if there are any. At the moment, I cannot. Okay. So yeah, I just defined it. So right now, okay. Let me add this as a remark. Right. So if the groups, if these are finitely generated, so I think this comes from this fact that I am. This comes from the notes of. This comes from the notes of Agnes Mochi on the mini course, Chromatic mini course. Yeah, I think I posted that the link in the group as well. So I think I got the remark from there. Okay, yeah, if it was finitely generated, then again, I don't have a piece of paper if I don't remember this. Yeah, I think this is it. And then the p-completion of X. Now, yeah, this is what I mean by the p-completion. P-completion of X. Right. So, okay, so maybe a definition. Spectrum is connect if phi L is equals to 0 for L is 0. Yeah, then we can check this. So this is the Heidelberg spectra. Yeah. Right. So as promised, so yeah, I see that I'm already over an hour. So yeah, let me see. Okay. Yeah, I'll just define the things. Yeah, and yeah, just as an example, we'll talk more about the telescope conjecture as well later on. But this is telescopic localization. This is an example, and yeah, that'll be it for today, I guess. After this, right? So yeah, there are a lot of things about. So yeah, I'll use the periodicity theorem that we have not seen. So yeah, a lot of stuff that we have not seen. So yeah, so just calm down. Don't need to worry about it. So just as an example, so P is a prime number and A is a finite P local spectrum. Yeah, we've not define anything, but bear with me. It's a finite local P local spectrum. So yeah, using the periodicity theorem, we'll have this self maps. I hope I am not messing this up. Right. Okay. Then the telescopic localization of X would be, right, is the homotopy co-limit. So that will be the homotopy co-limit of this. So yeah, just, as I said, just an example. We'll talk more about, we'll see telescopic localization a bit later. Right. So yeah, so that was my part. So right, I'd like to stop here. Thanks everyone for listening. maybe I can stop the recording now.